All right, so we'll continue where we left off yesterday. Again, let me know if you guys have any questions. You can speak through your audio or you can write on the chat, whichever you prefer. So today we're going to finish up 3.3. So let's revisit our notes from last time. So we talked about what if you have a differential equation, second order, constant coefficients, homogeneous in this particular form. So again, we're assuming that the solution is y equals e to the rt. And now this characteristic might possibly have a complex solutions, right, for r. So that means you have to know how do you express these solutions which has complex form for r, right? So that's the idea we're getting to. So we're in case 2 where our roots are b squared minus 4ac happens to be negative, okay? So we talked about a little bit of what are complex numbers. So complex numbers are in the form of alpha plus and minus beta I. So they always come in a conjugate pair, okay? So if you know alpha plus beta I is a solution, then alpha minus beta I is also a solution because they always come as conjugate pairs. And then we kind of talked about how to rewrite that imaginary part. I happens to be square root of -1, and then you can kind of take powers, different powers of I square, I cube, I fourth, I to the fifth, and I to the sixth, and so on. And you see how the pattern starts to change, and this is what we're going to use to derive what we're going to call it Euler's formula or Euler's identity. So that's what we're up to today. I'm going to show you how to express our solution if it is in complex root. So we're continuing with 3.3. Continuing with 3.3. So we're looking at y double prime, suppose it has a coefficient, plus b y prime plus cy equals to 0. Okay. So I am recording this session. It's recording in a different different thing, whatever it's called. Because it gives you a better resolution. I figured that out last night, so I'm going to continue to do it that way, okay? So you'll find it in my YouTube channel. I'll post them after I'm done with the session today. The usual. Okay, so we're looking at a second order homogeneous constant coefficient differential equation, and the characteristic polynomial of this is going to be ar squared plus br plus c equals to 0, and we're in the case where the roots are complex. So here we have complex root. So this is the case 3 that we're talking about. So r is equal to so let's say r1 and r2, two roots, right? It's a second degree polynomial. It's going to be alpha plus and minus beta I. So that means the solution that we assume was y equals e to the rt. Well, if r is complex, then our solution would then look like y equals e to the alpha plus and minus beta I t. That's how it would look like, right? Now the idea is we want to simplify this. We wanted to rewrite this. So if I were to rewrite using laws of exponents, we have e to the alpha t times e to the plus and minus beta I t by laws of exponents, right? Now the idea here is to simplify this portion that contains the complex number I. Okay, so that's the idea, and this is when we want to use Euler's identity. So I'm going to show you how to prove Euler's identity, but again, you don't have to know the proof, you just have to know the formula. but it's always good to understand where things are coming from, okay? So this is where we're going to recall some of the materials from power series that I asked you to look over last night. So if you did, all of this will make much more sense. If you didn't, it should make sense. Just make sure you follow through and let me know if you have questions. So we want to derive Euler's identity, or formula if you want to call it. So what is the Euler's identity? Okay, so let's derive the formula. So if you recall from calculus, what's the power series representation for e to the x? Do you guys remember this?
It's summation from n from like 0 to infinity, and then x raised to the n power over the n factorial.
Yep, absolutely. So this is the infinite sum starting at n equals 0 to infinity, x to the n over n factorial. So was it Sadia? Okay. All right. So I just want to remember everyone's name. So when you participate, it's good that I can recall some of your names. So thank you, Sadia H. So, and this is defined everywhere on the real line. So negative infinity to infinity, right? Now, I'm going to modify this just a little bit. What if we want to know the formula for e to the ix? What do you think that's going to be looking like? So if you just use the power series for e to the x, this would just be the sum, again, starting from n equals 0 to infinity. Now we're going to have, instead of x to the n, we'll have ix to the n over n factorial, right? Because I replace x with ix, so it just modifies that summation. So now what I'm going to do, I'm going to expand the summation and write out some of the terms, okay? So another way to write this summation would be the following way. You would have n equals 0 to infinity. You get I to the nth power, x to the nth power over n factorial. Again, laws of exponents, okay? And now I'm going to write out some of the terms and kind of group them in such a way so that it becomes more familiar to us. So when n equals 0, we have I to the 0th power, that's 1, x to the 0, that's also 1, and 0 factorial, that's also 1. So the first term is 1. Now what about the second term when n is equal to 1? So when n is equal to 1, we have I to the 1 power, x to the 1 power over 1 factorial. And then when n is equal to 2, we have I square x square over 2 factorial. N is equal to 3, we have I cube x cube over 3 factorial plus 4th x to the 4th over 4 factorial. So I'm going to write down just a few more, okay? So let's do n equals 5. So we have I to the 5th x to the 5th over 5th factorial plus I to the 6th x to the 6th over 6 factorial, and of course there are more terms. I think this is good enough to get to the idea where I'm heading, okay? So what I did, I wrote out the 7th term of this infinite sum, and the rest I wrote down as plus dot dot dot, okay? And now I'm going to use the simplification we did last class. So this was the purpose of me writing down the powers of I. So if I is raised to a 1 power, that's just I square is negative 1, I cube is negative I, and so on. So I'm going to apply these for this summation so I can simplify. So I'm going to rewrite this term, this one, and this one. Okay? So this is how it's going to look like now. So we have 1 plus, so ix over 1 factorial. 1 factorial is again 1. So this is just I times x. And then I square was negative 1. So this is negative x squared over 2 factorial. Okay? And then what was I cubed? Do you guys remember? So, negative, right? So I cube is negative I, so we have x cubed over 3 factorial, and I to the fourth, that's positive 1, so we have plus x to the 4 over 4 factorial, and then I to the fifth, if you remember, that was I, so this would be plus I x to the fifth over fifth factorial, and the last one, I to the sixth, that's going to be negative 1, so that's negative x to the 6 over 6 factorial. So just double check that one. Yeah. Okay. And then, of course, we have more terms after that. And now I'm going to group them by looking at like terms. So I'm going to combine terms involving I in one parenthesis and terms without I into another parenthesis. Okay? So the terms that involves I is this one, and this one. So they're going to be grouped into one single parenthesis, and then the rest will be into another one. So we have the following. We have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial and minus x to the 6 over 6 factorial. And of course, there are more terms. So these are the terms that don't involve I. Plus, now I'm going to write down the terms that involve I, and I'm going to factor out I as well. So we have I times, so the first one will just be x, and the second one would be negative x cubed over 3 factorial plus x to the fifth over 5 factorial. And there are more terms that I didn't write down, but this is good enough to explain. All right, so here we go. Now this should look familiar. What do you guys notice? So, Carolyn, do you notice anything? A plus bi. Yes, but I'm thinking in terms of familiar series. So, let's check. Thank you. I just picked on someone at random. I hope you guys don't mind. Bethany, what do you think? What do you think about this expression? So this one right here.
Isn't it like sine or cosine? I'm not sure which one.
Yeah, so you're right. It looks like sine or cosine, right? Now which one is which? So the first one that I highlighted, this one has even powers, right? So cosine, yeah. So thank you guys. So you can see that the first infinite series that we wrote out, this is just the series expansion for cosine of x plus I, and the last one, it has odd powers, and that's the expansion for sine series. Okay, so that would be sine of x. So this is the formula for e to the ix. And this is the formula that I want you to remember. This is what we call Euler's identity. Okay, so that's the magical identity we were after. So this is Euler's identity. So the derivation really comes from power series. And just rewriting e to the x using ix and expanding it out and then rewriting what are the I powers could represent, and then grouping the terms together in this form, you get sine and cosine series. And that would be a way for us to rewrite anything. If you have e to the ix, you can write it as cosine x plus I sine x. So, so this is the idea we're going to apply for this part of the complex solution we're going to arrive at. Okay. Now, before I get into more on how to write the solution, let's just do a quick examples on how do you really use this formula. Okay. So let's do the following example. So what is e to the I pi over 2? So using Euler's identity, we can simplify this. So the identity says if you have e to I times whatever, you do cosine of that plus I sine of that. So here my x is replacing sort of like pi over 2. So I can rewrite this as cosine of pi over 2 plus I sine of pi over 2 by using Euler's formula. Okay? Now you have to remember what is cosine of pi over 2. So that's taking us back to pre-calculus when you study trig functions.
Cosine of pi over 2 is 0.
Cosine of pi over 2 is 0. And what is sine of pi over 2?
1.
So therefore, yeah, question?
Sine pi over 2, isn't that 0?
No, that's 1. So if you recall the unit circle, right? Pi over 2 is right here. This is 0, this is pi over 2, this is pi, this is 3 pi over 2, and back to 2 pi. This coordinate is 0, 1, right? So sine represents the y coordinate, and x represents cosine. The x coordinate is cosine, right? Yeah. So e to the I times pi over 2 is really the number I. So that's pretty cool, right? You can express any form of an exponential in this form using Euler's identity. So let's do another one. So what if I give you, say, e to the I times 3 pi over 2? So I'm just going to rewrite this. The exponents is too tiny. So what if we want to rewrite e to the I times 3 pi over 2? So again, x is 3 pi over 2 in this case, right? So using Euler's identity, so give you a few seconds. Okay, so this would be what? Cosine of, yeah, that sounds right. So 3 pi over 2 is located right here. And this coordinate is 0, negative 1. And then you write this as cosine of 3 pi over 2 plus I sine of 3 pi over 2. And then again, looking at the unit circle, we get these exact values. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2, negative 1. So this is negative I. Okay, so that would be the evaluation for these trig functions. So let's do one more, right? So what if you have, say, e to the wrong color, black. Let's do e to the I, and then 5 pi over 4. So let's do that one. So I'll give you a few seconds to write this down. So again, using Euler's identity, this would be cosine of 5 pi over 4 plus I sine of 5 pi over 4, right? So that's applying Euler identity. Yep, so Liana, that's absolutely right. And now the next thing is we want to evaluate this, right? So we're going to do some pre-calculus. So 5 pi over 4, so if you look at the unit circle, it's located right here. So it's not on the standard position, right? It's not on the x, y axis, x or the y axis. So we kind of have to find its reference angle. That's something you should have done pre-calculus or in algebra, and then find its exact value. So in this quadrant, our x coordinate is negative, and our y coordinate is also negative, right? So that means we're going to get negative values for sine and cosine. So this is equivalent to cosine of negative pi over 4, that's its reference angle, plus negative I, so this looks weird, I shouldn't write plus and minus, can just put minus. So we have minus I sine of, again the reference angle is pi over 4. And now we can evaluate what is cosine of pi over 4. So if you remember from, again, pre-algebra or pre-calculus, this is negative square root of 2 over 2 minus I square root of 2 over 2. So that's the that will be the expression for e to the I 5 pi over 4. Okay. So any questions on this? So just a quick practice on how to use Euler's identity. Now we want to use this idea on our solutions to the differential equations where the root happen to be a complex conjugate, right? So this is what we're going to do. So if R is alpha plus or minus beta I, then the solution would be y equals e to the rt, well, r is now alpha plus and minus beta I times t, right? Now, again, by laws of exponent, I rewrote this as e to the alpha t times e to the plus and minus beta I t, right? And now, well, what is plus and minus beta I t? Well, that's when you're going to use Euler's formula, right? So this is really can be rewritten as e to the alpha t times cosine of, so I'm keeping plus and minus, but again, I'm going to modify this in the future. Plus and minus beta t plus and plus I sine of plus and minus. Actually, let me tell you this right now. It's okay to ignore that, okay? And I'm going to show you why it's okay to ignore this. So plus beta t plus beta t. So that's how our solution would look like if the roots are complex. So any questions up to this point? So do you guys see how I applied Euler's formula for the second part of the exponential right here? Does this make sense? Okay, so let me do an example and then I will show you why it's okay to ignore plus and minus, okay? So let's do a quick example before we jump to more theoretical stuff. So here's our first example for this. So let's solve the differential equation y double prime plus y equals to 0, okay? So I want to solve this equation. That means I'm looking for solutions. So we go ahead and write our characteristic polynomial. So our characteristic polynomial of this is going to be what? So someone tell me the characteristic polynomial. Carolyn, can you tell me the characteristic polynomial for this?
R squared plus R plus
1, yes. Thank you. So this would be r squared plus 1 equals to 0, right? So, and then if you try to solve this, you would notice that r is a complex value, right? So we can do r squared is equal to -1, and we take the square root, the usual, right? So we get r is equal to plus and minus I. So we get roots to be a complex number. So if I were to write this in alpha plus and minus beta I from, this is just 0 plus and minus I, right? Where alpha is this value and beta is this value. Sorry, not that. Beta is just 1, right? So that's this one. That's beta. So now we just plug this into our solution, which is e to the alpha t. So we have y is equal to e to the alpha t times cosine of beta t plus I sine of beta t, right? But because it's the general solution, so we need to multiply by this by our constants c1 and c2. So I'm going to break this down into a little bit more before we get to the general solution. So you can think of it this way. The first solution is the one with cosine, and the second solution is the one with sine. So really what we have as our general solution is y equals e to the 0 is just 1. So the alpha term sort of disappear. So we have c1 cosine of beta is also 1, t plus another constant c2 sine of beta, which is 1 t. So that will be our general solution for this. Okay. So any questions for this? So if the roots are complex, the solution would involve sine and cosine, their linear combination, right? And you will have the exponential term, but if alpha is 0, then the exponential term just go to 1. Let's do another one. And then I will explain why plus and minus is okay to ignore. So let's compute the general solution. So let's say we have y double prime minus 2y prime plus 2y equals to 0. So I'll give you all a minute to work on this, and then I'll probably call on someone. So tell me the characteristic polynomial for this.
R squared minus 2r plus 2.
Yep, thank you. So that's the characteristic polynomial. And now from here, you try to factor or you try to use the quadratic formula. Now this one doesn't factor, right? There is no way we can find two numbers to give us 2 same time adding up to -2. So that's not possible in the real line. So we're going to go ahead and use the quadratic formula, right? The famous quadratic. So r is equal to negative b, so that's negative, negative, positive 2, plus and minus square root of b squared, so that's 4, minus 4a is 1, c is 2, everything over 2 times a. Okay, so we have 2 over 2 plus and minus. So 4 minus 8, that's negative 4. So we have a negative 4 inside the radical. So that's why we run into complex solution, right? So we have 1 plus and minus. What's the square root of negative 4? Right, so it's 2i, and we then divide by 2, so that will just be I. Okay? So any question here? So Ambrose, it's not 4i, 2i, right? Because you're taking the square root of 4, which is 2, and then the square root of negative 1 is I. So I'm really simplifying this part. So this can be written as square root of negative 1 times square root of 4, which is I times 2. Okay? And divided by 2, so alright, same row, so you got it. Good. So now, what is alpha and what is beta? So alpha is 1, and what is beta? That's also 1, right? So now we just plug it into our solution for complex form. So our solution is going to be e to the alpha, which is 1, plus and minus beta 1 times t. And then we want to write this using Euler's identity. So we have y is equal to e to the t times cosine t plus I sine of t. Okay, so, but to write the general solution, we're going to put in constants c1 and c2. Okay, so this would be I sine of t. So our general solution is going to be y equals c1 e to the t cosine t plus c2 e to the t sine t. So that would be the general solution. Okay, so you can jump right to the general solution. You don't have to show all the steps that I did previous to. Those you can ignore. Once you know if it's a complex root, well, e to the alpha times cosine beta t plus sine of beta t. So you can always write those out. So any questions up to here? Okay, so, and then from here, if I give you initial conditions, you can plug those in as well. Okay, now I'm going to take you back to this part right here where I said it's okay to ignore plus and minus beta I. Why is it okay to ignore? Right, so let's explain the last part. So here we said that if the solution is in complex, if the roots are complex, then the solution would be e to the alpha plus and minus beta times t. And then by using laws of exponent, I rewrote e to the t. And so here I rewrote this part. I expanded this as e to the t times e to the, again, plus and minus I can ignore, it. Well, it, I apply Euler's identity, so that would be e to the t times cosine t plus I sine t, right? That's using Euler's identity. Now here, to get to the general solution, meaning we want all the solution, you have to bring in your constants c1 and c2. So you can think of cosine times the exponential is y1, and sine times the exponential is y2. So we have c1 e to the t cosine t, that's one solution, and c2 e to the t sine of t, that's the second solution. So you can think of this as y1 and this as y2, and their linear combination will form the general solution. Okay? So, does that make sense? All right. Okay. Now I'm going to go back and explain why it's okay to ignore plus and minus for beta t. So let's give you a tiny proof, an illustration. Why is it that we often do that? So let R1 be equal to alpha plus beta I, right? And let R2 be equal to alpha minus beta I. Because together we have R is equal to plus and minus beta I. Okay? Now we want the general solution. So our general solution, the general solution has the form y equals c1 e to the r1t plus c2 e to the r2t, right? But r1 and r2 are complex, so let's plug those in. So we have c1 e to the r1, well, r1 is alpha plus beta I times t plus c2 e to the r2. r2 is alpha minus beta I times t. Okay, so just plugging those in. Now here I'm going to use laws of exponent to split up the exponentials. So we have c1 e to the alpha t times e to the positive beta I t plus, now second one again using laws of exponents, we have e to the alpha t times e to the negative beta I t. Okay? And now here, we just discovered that this can be rewritten using Euler's identity, right? So that's what I'm going to do now. Now here I'm going to use, so apply Euler's identity. So if I do that, I get the following expression. And now I'm also going to factor out e to the alpha t, because that's common from both terms, okay? So I'm going to factor out e to the alpha t and rewrite the inside using Euler's identity. So for the first term, we have c1 e to the beta it, that's going to be cosine of beta t plus plus c1, right, I sine of beta t. So that's for the first term only. And now for the second one, I'm going to do the same thing. I'm going to rewrite e to the negative I beta t using Euler's identity. So I'm going to have plus c2 cosine of negative beta t plus c2 sine of negative beta t. So all of that is inside the big parentheses and expanded out using Euler's identity. Let me know if you guys have questions. Well, now here I'm going to simplify a little bit, okay? So I'm going to use some of the trig identity that you should have seen in the past. If you haven't, I guess that's okay. So if you recall, cosine of negative angle is cosine of positive angle. That's one of the identity that you should have known. Another identity is sine of a negative angle is negative sine of positive angle. That's from the past. Have you guys seen that more in the past? Did I miss an I? Let's check. Yeah, I did. Thank you. Right? I missed an I. All right. So now let's group this a little bit more and make it prettier. All right, it's going to become really nice. So let's keep going. So we have e to the alpha t is waiting outside. And now here's the thing. I'm going to simplify a little bit more. Here I have I times C1. Well, I is a constant, C1 is a constant, right? So do you agree I can just write that as a constant C1? I can just write it as another constant C1. Do you agree with that? Right? If you're multiplying two constants, you can always put them together and write it as another constant. If you're adding more than one constant, you can put them together. So this one and this one, I'm going to join them, and I'm just going to call them as a C1 and C2, okay? So here's how the next step would look like. So we have, and then I'm going to use this identity that I wrote down on the left, recall. So cosine of negative beta, okay? So I'm looking at this one right here. So using the identity on the left, cosine of negative angle, it's same thing as looking at cosine of positive angle. So I'm just going to write that as a cosine of positive angle. So we have the following. We have C1 plus C2, and they both share a cosine beta t. Okay? So I group those two together. Now for the sine terms, so I have C1 and C2, so I'm going to call this one C1. I'm going to call this one C2. Now, from the left side, I wrote cosine of negative angle. You can pull out the negative because sine is an odd function. So I can pull that negative out. So I'm going to have C1 minus C2, and they all share cosine beta t. So that's what we get by applying identities and grouping the constants together. Okay? Now, do you agree that I can just call this one constant, call this one just another constant, because I'm adding and subtracting constants, right? So what I'm going to do, I'm going to recall them a different constant. So I have e to the alpha t times c1 cosine of beta t plus, and then c1 minus c2, I'm just going to call it another constant, call it c2 sine of beta t. So that's our final solution. So that's why I said it's okay if you ignore plus and minus, because eventually they're already included within it because of these identities. Okay, so that's the derivation I wanted to show you. So let me know if you guys have any questions for this. Okay, are you guys following? All right. Okay, so let's do another problem. Let's do an initial value problem. Okay. So let's do this problem. This is example 3. So solve the initial value problem. So say we have y double prime plus 2y prime plus 5y equals to 0 with the initial conditions. Y of 0 is 5 and y prime of 0 is negative 3. Okay, so I'll give you guys a minute to work on this. Okay, so let's start. So what is our characteristic polynomial?
It's gonna be r squared plus 2r plus 5y is equal to 0.
Okay, and what are the roots?
I have negative 1 plus or minus I2. You have to use the quadratic formula.
Okay, so r is equal to -1 plus and minus 2i. Okay, so all of you should have gotten this. So you would get this by using quadratic formula. Okay, so we know alpha is -1, beta is 2, so we just plug it into our solution form. So we know our solution is going to be c1 e to the alpha t, so that's -1t. So I'm just going to write -t because it's silly to write -1t. -t cosine of beta t, beta is 2, plus c2 e to the alpha t sine of beta t, that's 2t. So that's the general solution, right? Now we're going to apply our initial conditions to y and its derivative and see if we can find c1 and c2. So let me know up to here if you have any questions. Okay? Uh, if you don't have questions, moving on to solving for c1 and c2. So y is equal to this. Let's take its derivative so that we can just go ahead and plug them in. Oh, okay. So we'll be doing some product rule. So negative, let's see, negative c1 e to the negative t cosine of 2t. The derivative of cosine is negative, so that's negative c1 e to the negative t sine, so 2 c1 sine of 2t. So that's the derivative of the first function. Now the second one, again, we use product rule, so that would give us okay, sorry guys, I think I'm taking the long way to solve this. But you could have go ahead and plug in y of 0 is 5, and maybe we can do something better. Okay, I'm just going to go ahead and take the derivatives. Let's see what happens, okay? So, uh, so if I take the derivative of the second function, I have negative c2 e to the negative t sine of 2t, and then plus 2c2 e to the negative t cosine of 2t. Okay, so we took the derivatives of y, and let's see what happens when we plug in these initial conditions. So y of 0 is 5, so that means we're plugging in t is equal to 0 and y is 5. So y is equal to, so when t is 0, sine of 0 is 0, so the sine term will disappear. So we only have c1 e to the 0 is 1, cosine of 0 is 1, so c1 is 5. Oh, that's nice. Okay, cool. Now, second condition, we have y prime of 0 is equal to -3. So that means we plug in t is equal to 0. So that means all the terms involving sine will go to 0. So we know this will go to 0. This will go to 0. So the last one and the first one will survive. So let's write those out. So we have -3 is equal to negative c1 e to the 0 is 1, cosine of 0 is also 1, so that's just negative c1, and the last one we have plus 2c2 e to the 0 is 1, cosine of 0 is also 1. And we know C1, we just solved it. That's 5. So we have negative 3 is equal to negative 5 plus 2 C2. So we have 2 is equal to 2 C2. So C2 is equal to 1. Okay, that wasn't so bad. So what is our solution? So hence, our solution to this is y equals C1, that's 5, e to the negative t cosine of 2t plus C2, that's 1, e to the negative t sine of 2t. So that will be our solution to this problem. Any questions? Alright, so that will be our solution to this. Okay. So let me know if you guys have any questions. So that's 3.3. Okay. Now the next section we're going to talk about is 3.4. So that's the last case that we are going to run through. Now, so we've seen solution when the roots are real, distinct, meaning R1 is not equal to R2. And then we just saw solutions when the roots are complex. We know how to express them. And now, what if the roots are equal, meaning R1 is exactly equal to R2? How would the solution look like? So that's the next thing. So moving on to section 3.4. So 3.4 is repeated roots. And reduction of order. Okay, so we're going to use reduction of order to derive the solutions if the roots are repeated. Okay, so I'll again give you an illustration, a little bit of background, how to derive the solution, but at the end you just have to remember the formula. Okay, so now the big question is, so here's the big question. What if the roots are repeated? That's the big question, right? Meaning we're looking at R1 is exactly equal to R2. So we're in the third scenario. So going back to our notes from last class. So third scenario is right here. If b squared minus 4ac is equal to 0. Meaning the radicand is 0. So all we're left with is negative b over 2a. So there's no plus and minus coming into the picture. That means you're only getting one root for the solution. It's a quadratic, so we're expected two solutions, not just one. So it is repeated roots. Okay, so let's look at it and give you an illustration how to get to the solution. So suppose I want to solve the following differential equation. So here's an example. So let's solve y double prime plus 4y prime plus 4y equals to 0. Okay, so we want to solve this. So the usual way, you write out its characteristic polynomial, you assume the solution is e to the rt, right? So our characteristic polynomial for this would be r squared plus 4r plus 4. So I wrote the 4 backwards, sorry. Plus 4, right, equals to 0. And then we can factor this. This is r plus 2 squared equals 0. And then if you take the square root and subtract 2, you get r is equal to -2. Well, hey, we only got one root, but it's a second degree polynomial. So where's the other root, right? But the other root is also -2. So r1 is exactly equal to r2, which is -2. So it is real and repeated. Okay, so that's what it means when the roots are repeated. So that means we only know one solution. We only know how to write one solution. y1 is equal to e to the -2. Well, now the big question is, what is the second solution, right? So we want to find how would the second solution look like if the roots are repeated, because we only know one solution to this because we only computed one value for r. So this is where I'm going to show you the illustration. How do we derive the second solution using the Alembert's method, which is also called the reduction of order. Okay, so let's get to the illustration, and then I'll give you what is this second magical solution. Okay, so how do we find y2? That's the question. Well, we will be using, so we will use the Alembert's method. I think that's how you spell his name. I could be misspelling his name. The Alembert method, which is also called reduction of order. So the reason I give you the mathematician's name, because we should always honor these people, because they work through a lot for us to really get to this far. So they should be honored for that. Okay. So, but the method is really reduction of order that we're going to use to seek the second solution. Okay. So how does it work? Well, this is how it works. So we know y1 is a solution. So c1 times y1 is also a solution, right? Constant times y1 is a solution. So since y1 is a solution to the differential equation, we know that constant time y1 is also a solution, right? So c1, or just call it c. For now, let's call it just constant c. c times y1 is also a solution. So what D'Alembert said, what if you replace the constant with a function? Okay, so that's the idea. We're going to replace the constant c with a function. Let's call it v of t, okay, or v of x if your independent variable is x. So then we're trying to determine what is this function v. What is v of t? That's the idea, because that will give us the solution to this. So we're going to go ahead and start with the following assumption. To find v of t, we're going to assume that our general solution is going to be y equals v of t times y1. Okay, that's the assumption we're going to make. So that means we just need to find what is v of t, and then that will give us the answer to our big question. Well, so let's proceed to the method. If we know general solution is v times y1, that means I have to compute its first derivative, second derivative, and plug it in to the original equation, right? So that's what we're going to do. So I'm going to plug in. So before I plug in, I'm going to substitute my solution y1, which is, we computed right here, that was e to the negative 2. E to the negative 2t. I'm going to substitute this into our general solution and compute its derivative. So then we have y is equal to v times e to the negative 2t. And then y prime is going to be so because v is a function, you have to use product rule. So we have v prime e to the negative 2t plus minus 2v e to the negative 2t. So that's y prime. And we have to compute y double prime because our equation involves second derivative. So to compute the second derivative, we use product rule again. So we have v double prime e to the negative 2t, then minus 2v prime e to the negative 2t. And now differentiate the second piece. We have negative 2v prime e to the negative 2t plus 4v e to the negative 2t. Okay? Let me know if you guys have any questions. Well, now here I can combine before I plug them in, right? So my y double prime will be v double prime e to the negative 2t. And then here we have like terms. This one and this one, they are like terms. So I will combine them, negative 4 v prime e to the negative 2t. And the last one we have 4v e to the negative 2t. Okay? Okay. Do you guys have any questions so far? All right. Okay, so I have an expression for y prime, y double prime. I'm going to plug those into the original and see what we can get. So our original equation is right here. Y double prime plus 4y prime plus 4y. So we have y double prime, that's going to be v double prime e to the negative 2t minus 4v e to the negative 2t plus 4v e to the negative 2t. And then plus 4 times y prime. Y prime is this expression on top. We have v prime e to the negative 2t minus 2v e to the negative 2t. And then plus 4 times y. Well, y is just the assumption we made. That was v e to the negative 2t. Everything equals to 0. Okay? And now we just simplify this and hopefully we get something nice. So what I did was I substituted y double prime, y prime, and y into the original. And that's how I got this part. Well, now I'm going to go ahead and try to simplify this. So if you look closely to this equation, I have 4v prime. So it looks like I made a typo. This should have been v prime. Okay? Yeah, so that's the typo I made. So if you look closely now, this one and this one, after you distribute, they cancel out, right? Yeah. And then what else happens? Yeah, right? Right, so this one also cancels out. Yep. Sorry, it took me a while to see it. This one, when you distribute the the 4 cancels out with this and that together. Okay, so thank you. So we're only left with v double prime e to the negative 2t equals to 0. Well, then we just simplify this, right? Divide e to the negative 2t, we have v double prime is equal to 0. Now, from here, we can integrate, right? So that we can find the function v. So I'm going to go ahead and integrate once. So I have v prime. That's just going to be a constant c1, right? Because when you differentiate, you get 0. And then I'm going to integrate one more time. So that will give me v is equals to c1t plus c2. So that's our magical function v. That's pretty cool, right? Okay, so what is the solution we're after? We know that our general solution is going to be y equals v times y1. So this would give us y equals v, which is c1t plus c2 times y1. y1 we computed to be e to the negative 2 for this scenario. So that's e to the negative 2. And then by multiplying this, we have c1t e to the negative 2t plus c2 e to the negative 2t. That's the general solution. But the question was, what is the second solution? Now, from the general solution, you can collect the first solution and the second solution. So the first solution should be clear to you. That's this piece right here. That was y1. So that means this has to be y2. Okay? So the conclusion is, if you know the first solution, then the second solution is just a function t times the first solution. That's how you get the second solution if the roots are repeated. Okay? So any questions on this? So in conclusion, so if the roots are repeated, then uh, y1 is equal to e to the rt. R1 and R2 are equal, right? So that's what repeated means. R1 is equal to R2. Y1 is equal to that. That means Y2 is going to be t times e to the rt. You just multiply the first solution by a function t. That's the conclusion we're going to draw. So any questions on reduction of order? So this is the method you have to remember, because sometimes you'll be given equations that are not just repeated roots, we're missing one of the solution. And you're given one solution, you have to compute the second solution. So you would go through this method, which we can call it the Alembert's method, or reduction of order, to compute the second missing solution. Okay, so the method is useful, and we saw the method is useful for this case where the roots are repeated, and it's also useful when you have to compute the second solution if the first solution is missing. Okay, so this is just the conclusion if the roots are repeated, not just in general. Okay, so let me know if you guys have any questions.
Professor,
Yep.
for this question, couldn't have we used Abel's theorem?
Yeah, that's the second method. You could also use Abel's theorem to compute the second independent solution. Yep.
Would it be like more complicated than?
No, it wouldn't be more complicated, but you have to know how to use reduction of order.
Okay.
Yeah, so I will show you how to use also the, not the Alembert's, this is the Abel's method, so that you know how to use both. Okay. So, all right, so let's do another example for 3.4. So here's another example. So let's solve. Uh, so let's do y double prime minus y prime plus 1/4 y equals 0. So we will go ahead and write the characteristic polynomial for this. Okay, so we have r squared minus r plus 1/4 equals to 0. If you don't like fractions, you can go ahead and multiply both sides by 4, get rid of the fraction, but I'm just going to go ahead and factor this. So I can factor this into r minus 1/2 squared equals 0. I think that will do. Yep, that works. So that means we have r1 is equal to r2, which happens to be 1/2. So we have real repeated, right? Repeated roots. So what is our solution to this? Our solution is c1 e to the rt, that's 1/2 t, plus c2. Well, the second solution will just be multiplied by t times e to the 1/2 t. So that will be the solution to this. Any questions? Okay, any questions on repeated roots? Okay, so if there are no questions, let me give you another problem where you have to use reduction of order to get to the second solution. Okay, so here is an example. So let me start off by giving you the differential equation. So given t squared y double prime minus 2t y prime minus 10y equals to 0 for t greater than 0, assume y1 is equal to t to the 5th power is a solution. Okay, and find another linearly independent solution. To y1. So you're given a random differential equation that we haven't really learned how to solve because it has function coefficients. But you're told that you know one of the solution and you have to find the second solution, which is linearly independent from the first solution. This is the scenario. So the hint is, if you know one solution, you can always find the general solution, and from there you can pick up which one is y1 and which one is y2, right? So the way we're going to approach this question is by using reduction of order. So any questions before I start? Okay, does it make sense where we're headed? Okay, so we're going to assume that our general solution is some function v times y1. So v is a function, right? V of t. So, and then plug in y1 because that's given to you. So y is equal to v times t to the 5th power, and then compute its first derivative, second derivative, and plug it in. So we have y prime, which is v prime t to the 5th plus 5 v t to the 4th. And now compute its second derivative. So we have v double prime t to the 5th plus 5 v prime t to the 4th, and then differentiate the second function of v prime, y prime. We get plus 5 v prime t to the 4th plus 20 v t to the 3rd. Okay, and then I can combine those terms in the middle. We have v double prime t to the 5th plus 10 v prime t to the 4th plus 20 v t to the 3rd. And now I'm going to go ahead and plug in the expression for y prime, y double prime into the original equation. Okay, so if I do that, I get the following. So we have t squared times y double prime. So that would be v double prime t to the 5th plus 10 v prime t to the 4th plus 20 v t to the 3rd. And in the second term, we have negative 2t times y prime, negative 2t times y prime. That would be v prime t to the 5th plus 5v t to the 4th. And the last term we have is minus 10 times y. That would be minus 10 times v t to the 5th. Everything equals to 0. And now here, once you finish plugging in, just collect terms, cancel things out, and see if you can solve it. Okay? So if I were to go ahead and continue and distribute, I have v double prime t to the 7th plus 10 v prime t to the 6th plus 20 v t to the 5th minus, and then here I'm going to distribute negative 2t, so I have 2 v prime t to the 6th minus 10 v t to the 5th minus 10v t to the 5th equals to 0. Let's see if we can simplify this. Okay, so this is the part you want to be extra careful. So
The 20 v t to the 5th and the negative 10 v to the 5th minus 10 v t to the 5th, they cancel out.
yep, so these will disappear. Oh, that's nice. Thank you. All right, so now the rest we just have to combine and add and subtract their coefficients. So we have v, so wrong color, v double prime t to the 7th, and then 10v prime t to the 6th minus 2v prime t to the 6th. That's plus 8v prime t to the 6th equals to 0. Okay, so that's nice and neat. Now because t is bigger than 0, we can go ahead and divide by t to the 7th. So we have v double prime plus 8 over t v prime equals to 0. Okay, so how do you think you're going to solve this? This should look familiar, right? So this should give you a hint to use the reduction of order we studied at the end of chapter 2. So here you have reduction of order again, or the other reduction of order. Right, so you come up with the substitution, so v is already there, I'm going to let w be equal to v prime. So that means W prime is V double prime, right? That was the reduction of order we studied at the end of chapter 2.9, so chapter 2. So if I do that following substitution, this is the differential equation I'm going to have. W prime plus 8 over T W equals to 0. And now, how do you solve this equation?
It can either be linear or separable.
Right, so you can use integrating factor or separation of variables. So I'm going to go ahead and use integrating factor. So mu of t is going to be e to the integral of 8 times 1 over t dt. So that's e to the 8 ln of t. That will be t to the 8. Okay, so then we have t to the 8 times w. Its derivative on the left side, and the right side is 0 times that. That's just 0. Wouldn't change much. And now we go ahead and integrate both sides. So we have the integral on the left side and on the right side. We have t to the 8 times w is equal to a constant. Let's call it C1. And then I can go ahead and divide by t to the 8 to solve for w. So we have w is equal to C1 t to the negative 8, because I divided and then I put it on top, makes the negative power. And now, well, what is w? W was v prime. So let's go ahead and plug in. So we have, no, wrong screen. Okay. So this would be v prime is equal to C1 t to the negative 8. And then to solve for v, we just have to integrate one more time. So we get v is equal to, and then we integrate on the right side as well. That would be C1 t to the negative 7 plus C2. So that's our function v. But that's not the second solution, right? We have to write out the general solution, and then from there we pick up which one is y1, the other one would be y2. So we know our solution, it's going to be y equals v times y1. Well, v is this function we computed, c1 t to the negative 7 plus c2. What was y1? T to the 5th. So let's multiply this by t to the 5th. And then we have y is equal to c1 t to the negative 2 plus c2 t to the 5th. So what is y2?
T to the negative 2.
Yep, because the other half is y1. So that's the second independent solution for this differential equation. We will learn how to solve these where the coefficients are functions, but that's in chapter 5, I believe. So we're not up there yet. But we can still compute solutions by just using reduction of order. Okay? Alright, so that's the end of 3.4. You could have computed the second solution to this by using the Alembert method, not this one. Sorry, not the Alembert. We did that. Abel's theorem. You can use that, but I will show you that next class. So, but if you want to try it out, you could do that. That's no big deal. But the idea is know how to use reduction of order. This is a very important concept for chapter 3.4. Okay. All right. So let me just sum this up. So here's a summary. It's a summary of second order linear differential equations. Homogeneous. Okay. So we're looking at the characteristic polynomial AR squared plus BR plus C equals to 0. That's the one we're looking at. So we have three cases. If R1 is not equal to R2, then our solution will have the form y equals C1 e to the R1t plus C2 e to the R2t. If the roots are distinct and real, right, that's how it would look like. The second case was 3.3. If R1 and R2 are complex, right? So they're complex conjugate. So that means our solution will look like y equals, so I like to write it this way, C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. Or you can factor out e to the alpha t, that's up to you. And the last case is if the roots are repeated. So if R1 is exactly equal to R2 and they're real repeated, so then our general solution would look like y equals C1 e to the RT plus C2 t e to the RT. So these are the three different cases you can run into if you're solving a second degree polynomial. Okay. All right, so that's the end of today's lesson. That's the end of 3.4. Now I'm going to give you a brief outline for what to be expected from exam 1. Okay, so let me know if you guys have questions before I start. So this is where I'm going to draw the line. So that's the end of 3.4. So for exam 1, you are responsible for the following sections. So the sections are going to be chapter 1, where you classified and slope fields, we talked about them. Chapter 2, everything we covered. And chapter 3, so we didn't finish chapter 3 because there's more to talk about. Only 3.1, 3.2, 3.3, and 3.4. So chapter 1, chapter 2, chapter 3 only up to 3.4, which is up to today's lesson. Now, so this is how I'm thinking of putting questions for this test. So we worked on classifications. So there's going to be a question on classification of differential equations and slope field. So know how to match a specific slope field with its differential equation. So you had a web work to help you with that. So something like that I might ask you. And then know how to solve first order. So for first order, we have 4 different methods to solve. We have separation of variables. So if it's separable, you use that. And then we had homogeneous. We use that substitution v is equal to v as a function of y over x. And then we talked about linear first order. So you had to use integrating factor to solve it. And the last method we had was exact. And along with all of these, I can input an initial value problem for you. Okay, so that's first order. And then after that, we talked about applications. So there's 2 types of application that you are responsible for. One, tank or salt. Second one is compound interest. So these are the 2 applications you are responsible for. I'm not going to put Newton's law of cooling because I didn't cover that. So if you had that on web work, that's totally fine. Extra practice is always good. So that's that. And then there could be a question on reduction of order. So within reduction of order, we had two different cases. If the independent variable is missing, if the dependent variable is missing. So those are the two scenarios we had. And we had Bernoulli equations. Okay, so know how to solve them. And then we moved on to second order. So for second order, we solved homogeneous, right? Second order differential equations. So that's all the three cases you can possibly have. If the roots are real, if the roots are complex, and if the roots are real repeated. So that could be one of them with an initial value. And then we talked about the Wronskian. Wronskian of two pair of solutions. And then, what else? Yeah. And then the last thing we had was reduction of order. So this one, if y1 is given, compute y2. So that's the second reduction of order we used for this section 3.4. And then along with them, know your theorems, right? So the important one were 3.2.1, 3.2.2, and I think the last one was Abel's theorem, which was 3.2.7, but let me just double check that for you. So you have all of it in my notes. So yeah, so 3.2.7, know this theorem, and then 3.2.2, which is the superposition principle, and the existence and uniqueness theorem as well. So yeah, so that's the outline for our exam. Any questions? Oh, how many questions, right? So I'm going to try to put about 10 to 12 questions. Okay, and you'll have the time will be 6:30 to 7:40. So you'll have 70 minutes for the test. Okay, so you'll come in and we'll have a lesson for 30 minutes, and then you'll start the test at 6:30, and you'll go on up to 7:40. So that will be the test. And then after the test is over, so during the test, I'll probably send you the link from Dropbox. You'll scan your work, right? Scan, no pictures, no pictures. Scan your work. And upload them in Dropbox. Link will be sent to your email. So whichever email you have on CUNY first, that will be the email I will be using to send you the link to Dropbox. All right, so any questions? All right, so I'm gonna stop our session for today.